While 300kcmil and 600kcmil are not commonly used sizes for power cables, there are instances where their use may be advantageous. When dealing with 300kcmil cables, one benefit is reduced voltage drop. 300kcmil cables have a lower resistance than smaller sizes, which can reduce voltage drop over long distances. Another potential advantage is transient protection. 300kcmil cables have higher reactance, which can provide transient protection against short-circuit currents. Furthermore, in some jurisdictions, 300kcmil cables may be required for certain applications, such as main feeder cables, due to code compliance requirements. Now turning to 600kcmil cables, one key advantage is high current capacity. 600kcmil cables can carry very high currents, which is suitable for large motors, generators, and other high-power applications. Another benefit is increased flexibility. 600kcmil cables are more flexible than larger sizes, making them easier to install in tight spaces. A third benefit could be future expansion. Using 600kcmil cables can provide the capacity for future expansion of the electrical system without the need to replace cables later. However, there are several considerations when thinking about using 300kcmil and 600kcmil cables. Firstly, availability. 300kcmil and 600kcmil cables may not be readily available from all manufacturers. Secondly, cost. These sizes are typically more expensive than more common sizes like 250kcmil or 500kcmil. Thirdly, terminations. Special terminations may be required for these odd sizes, which can add to the overall cost of the installation. Based on industry practices and code requirements, it is generally recommended to avoid using 300kcmil cables whenever possible. However, in specific cases where the advantages of 300kcmil or 600kcmil cables outweigh the disadvantages, their use may be justified. When considering the use of odd-size cables, it is always advisable to consult with an experienced electrical engineer or design professional to ensure compliance with code requirements and to evaluate the overall cost-benefit of the installation. Let's dive a bit deeper into the specific technical aspects related to these cable sizes. We can start by discussing ampacity, which is the current carrying capacity of a conductor, typically measured in amps. The ampacity of a cable is determined by several factors, including its size, insulation type, installation method, and ambient temperature. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors under different conditions. For example, NEC Table 310.16 provides ampacity values for insulated conductors rated up to 600 volts, installed in raceways or cables, and based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. The ampacity of a 300kcmil cable will vary depending on its insulation type and installation method. For example, a 300kcmil copper conductor with THHN insulation installed in a raceway has an ampacity of 285 amps according to NEC Table 310.16. Similarly, a 600kcmil copper conductor with THHN insulation installed in a raceway has an ampacity of 420 amps. These ampacity values are based on specific conditions, and it's crucial to apply correction factors for ambient temperatures above 30 degrees Celsius or when more than 3 current-carrying conductors are installed in a raceway. These correction factors reduce the allowable ampacity of the conductors to prevent overheating. Voltage drop is another critical factor to consider when selecting cable sizes, especially for long runs. Voltage drop occurs due to the resistance of a conductor, and it can negatively impact the performance of electrical equipment. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. The voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance, or volts equals amps times ohms. The resistance of a conductor depends on its material, length, and cross-sectional area. Larger conductors have lower resistance, which results in lower voltage drop. 300kcmil and 600kcmil cables are sometimes used to minimize voltage drop in long runs, even if their ampacity is higher than required. Reactance is another electrical property that can influence cable selection, particularly in alternating current or AC systems. Reactance is the opposition to the change of current flow, and it's caused by inductance and capacitance in the circuit. Inductive reactance is more prevalent in power cables, and it increases with frequency and conductor spacing. Cables with larger cross-sectional areas tend to have higher inductive reactance. In some cases, a higher reactance of 300kcmil cables can provide transient protection against short-circuit currents by limiting the rate of current rise. However, excessive reactance can also lead to voltage regulation problems and reduced power factor. Short-circuit current rating is an important consideration for cable selection to ensure the cable can withstand fault currents without being damaged. When a short circuit occurs, the current can reach very high levels, potentially causing the cable to overheat and fail. The short-circuit current rating of a cable depends on its size, insulation type, and the duration of the fault. The NEC requires electrical systems to be designed to withstand the available fault current at each point in the system. 300kcmil and 600kcmil cables generally have higher short-circuit current ratings compared to smaller sizes, providing better protection against fault currents. Flexibility is a practical consideration during cable installation, particularly in tight spaces or when routing cables around obstacles. Larger cables tend to be less flexible, making them more difficult to handle and install. 600kcmil cables are often preferred over larger sizes, such as 750kcmil or 1000kcmil, because they offer a good balance between current carrying capacity and flexibility. However, cable manufacturers have also developed more flexible cable designs that use stranded conductors and specialized insulation materials to improve flexibility without sacrificing performance. Cost is always a significant factor in electrical design and installation. 300kcmil and 600kcmil cables are typically more expensive than more common sizes like 250kcmil or 500kcmil. The cost difference can be attributed to the increased material required to manufacture these larger cables and the lower demand for these less common sizes. Additionally, special terminations and installation methods may be required for these odd-sized cables, which can further increase the overall cost of the installation. Availability can also be a limiting factor when considering the use of 300kcmil and 600kcmil cables. These sizes may not be readily available from all manufacturers or distributors, which can lead to longer lead times and higher prices. In some cases, it may be necessary to substitute with a different cable size or to use multiple smaller cables in parallel to achieve the required ampacity and voltage drop performance. Terminations are a critical aspect of cable installation, and they must be properly selected and installed to ensure a reliable and safe electrical connection. 300kcmil and 600kcmil cables may require special terminations, such as compression lugs or mechanical connectors, to accommodate their larger size and higher current carrying capacity. These terminations must be compatible with the cable material, insulation type, and the equipment to which the cable is connected. Improper terminations can lead to overheating, arcing, and eventual failure of the electrical connection. Code compliance is paramount in electrical installations, and the NEC provides comprehensive guidelines for cable selection, installation, and protection. The NEC specifies the minimum requirements for conductor ampacity, voltage drop, overcurrent protection, and grounding. It also addresses specific applications such as motor circuits, feeder circuits, and hazardous locations. Electrical engineers and contractors must be thoroughly familiar with the NEC and other applicable codes and standards to ensure that their installations meet all safety and performance requirements. When considering the use of 300kcmil and 600kcmil cables, it's essential to evaluate the specific application requirements and to consult with experienced professionals to ensure code compliance. Here are some additional points to consider regarding 300kcmil and 600kcmil cables. Firstly, harmonic currents. In electrical systems with nonlinear loads, such as electronic ballasts and variable frequency drives, harmonic currents can be a significant concern. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz in North America. These harmonic currents can cause overheating of conductors, transformers, and other electrical equipment. 300kcmil and 600kcmil cables may be used to mitigate the effects of harmonic currents by providing a lower impedance path for these currents to flow. Secondly, skin effect. Skin effect is a phenomenon in alternating current circuits where the current tends to flow more densely near the surface of the conductor. This effect becomes more pronounced at higher frequencies and with larger conductors. Skin effect can increase the effective resistance of the conductor, leading to increased voltage drop and power losses. 300kcmil and 600kcmil cables are more susceptible to skin effect compared to smaller conductors. Therefore, it's essential to consider this effect when designing systems with high-frequency currents. Thirdly, derating factors. The NEC requires that conductor ampacities be derated under certain conditions, such as when multiple conductors are bundled together or when the ambient temperature is high. These derating factors reduce the allowable ampacity of the conductors to prevent overheating. When using 300kcmil and 600kcmil cables, it's essential to apply the appropriate derating factors based on the specific installation conditions. Fourthly, parallel conductors. In some cases, it may be necessary to use multiple conductors in parallel to achieve the required ampacity for a particular circuit. The NEC allows for the use of parallel conductors, provided that certain conditions are met. When using parallel conductors, it's essential to ensure that all conductors are of the same material, size, and length, and that they are properly terminated to ensure equal current sharing. Fifthly, grounding and bonding. Proper grounding and bonding are critical for electrical safety. Grounding provides a low impedance path for fault currents to return to the source, which helps to protect people and equipment from electrical shock. Bonding ensures that all metal parts of the electrical system are electrically connected, which helps to minimize voltage differences and reduce the risk of shock. 300kcmil and 600kcmil cables may be used as grounding conductors or bonding jumpers in certain applications. Sixthly, cable trays and supports. Cable trays and supports are used to support and route cables in industrial and commercial buildings. The NEC provides guidelines for the proper installation of cable trays and supports, including requirements for spacing, support intervals, and bonding. When using 300kcmil and 600kcmil cables, it's essential to select cable trays and supports that are suitable for the size and weight of the cables. Seventh, cable pulling. Cable pulling is the process of installing cables in raceways or conduits. The NEC provides guidelines for cable pulling, including requirements for pulling tension, lubrication, and bending radius. When pulling 300kcmil and 600kcmil cables, it's essential to use proper pulling techniques and equipment to avoid damaging the cables. Eighth, cable insulation. Cable insulation is the material that surrounds the conductor and provides electrical insulation. Common insulation materials include THHN, THWN, XHHW, and RHH. Each insulation type has different properties, such as temperature rating, moisture resistance, and chemical resistance. When selecting 300kcmil and 600kcmil cables, it's essential to choose an insulation type that is suitable for the specific application and environmental conditions. Ninth, cable shielding. Cable shielding is used to reduce electromagnetic interference, or EMI, and radio frequency interference, or RFI. Shielded cables have a conductive layer, such as a copper braid or foil, that surrounds the insulated conductors. The shield is typically grounded to provide a path for unwanted noise currents to flow. 300kcmil and 600kcmil cables may be shielded in applications where EMI or RFI is a concern. 10th, cable glands and connectors. Cable glands and connectors are used to terminate cables at electrical equipment, such as junction boxes, enclosures, and panels. These fittings provide a secure and environmentally protected connection. When selecting cable glands and connectors for 300kcmil and 600kcmil cables, it's essential to choose fittings that are suitable for the cable size, insulation type, and environmental conditions. Also, consider the application in terms of motor starting. Large motors can draw very high inrush currents when they start, which can cause voltage dips and flickering lights. 600kcmil cables may be used to minimize voltage dips during motor starting by providing a lower impedance path for the inrush current. Also, consider emergency power systems. In emergency power systems, such as those used in hospitals and data centers, reliability is paramount. 300kcmil and 600kcmil cables may be used in critical circuits to ensure that they can handle the required load under emergency conditions. And variable frequency drives, or VFDs. VFD are used to control the speed of electric motors. VFD can generate harmonic currents which can cause problems with electrical equipment. 300kcmil and 600kcmil cables may be used to mitigate the effects of harmonic currents generated by VFD. Consider UPS systems or uninterruptible power supplies. UPS systems provide backup power in the event of a power outage. 300kcmil and 600kcmil cables may be used in UPS systems to ensure that they can handle the required load during a power outage. Also consider high-rise buildings. In high-rise buildings, voltage drop can be a significant concern due to the long cable runs. 300kcmil and 600kcmil cables may be used to minimize voltage drop in high-rise buildings. Also consider data centers. Data centers require a reliable and stable power supply to ensure that their equipment operates properly. 300kcmil and 600kcmil cables may be used in data centers to provide a reliable power supply. When selecting cables, consider the ambient temperature. High ambient temperatures can reduce the ampacity of cables. It is important to select cables that are rated for the expected ambient temperature. Also consider corrosion. In corrosive environments, it is important to select cables that are resistant to corrosion. Also consider mechanical stress. Cables that are subject to mechanical stress such as vibration or bending should be selected to withstand the stress. In summary, selecting the appropriate cable size involves a comprehensive evaluation of various factors, including ampacity, voltage drop, short circuit current rating, flexibility, cost, availability, termination requirements, and code compliance. While 300kcmil and 600kcmil cables may not be the most common choices, they can offer advantages in specific applications where their unique characteristics are beneficial. Consulting with experienced electrical engineers and design professionals is crucial to ensure that the selected cables meet all safety and performance requirements and are compliant with applicable codes and standards.